thank you for being here. So we have the pleasure today of receiving Amini. And Amini has completed his thesis at the École Normale Supérieure in Paris under the supervision of Marc Lelarge and François Bachelli. And then subsequently has worked at Swiss Finance Institute, applying his work on random graphs to problems that arise in finance. And today he's going to talk about joint work with Yuval Peres on first passage calculation and computing the shortest weight paths in random graphs. So,
okay, thank you. Thanks for the invitation. So I'm happy today to talk about the first passage calculation in random graphs. So we're going to study the impact of introducing edge weights on distances in random graphs. So we look at some applications also on rumor spreading problem, for example. So I'm going to present different plots. Going to points right, Marc Lelarge and Yuval Peres. We start by a brief introduction. So a network is a set of items or nodes, connection between them or connected. A lot of things in the world may turn out to be a network when we look at them in the right way. The examples include social networks, neural networks, biological networks, and many other things. Okay. So we'd like to start by rumor spreading problem. So assume that we have initially a piece of information based on one of the nodes of the graph G, that means vertex set B and edge set B. So the classical model was first investigated by Fried and Lumet in 1995. And so we have initially a piece of information from one node, and in each time step, every informed node sends the information to another node between neighbors, which he chooses uniformly at random. Okay. Then the question is how many time steps are needed to such that all nodes become uniform. So there are few models that we use this process, like rumors for computer viruses. These are process for example. So this model has been investigated in different geometry. So in massive geometry, there are results which show that this model is fast, which means that the time needed to inform small population is of order of log n when n is the side of the graph. For example, for complete graph, results by Fried, Lumet, and some other. And there are results on hypercubes and random graphs. And another kind of result is that the model is robust against transmission failure, so we can assume that some edge, for example, doesn't work. And there are results, for example, for the case of complete graph and random graphs that, again, time needed is of order of log n. Okay. So let us now consider a continuous time version of this rumor spreading model. So in continuous time, we assume that each node is endowed with the Poisson process with parameter 1, and such that at the instance of this Poisson process, the node wakes up and again contacts or infects one of its neighbors uniformly at random. Okay. Initially, one piece of information is based on one node, and then again we look at how much time needed to inform whole population. Okay. So note that the local dynamics are similar on average. With one node, average, the time needed to inform neighbor is at previous model. Okay. So the question is which one is faster? So what do you think? Continuous time version is faster or discrete time? So for general case, I don't know, but let us look at, for example, for regular graphs, random regular graphs. So random R regular graph. So random R regular graph. Assume that we have n nodes, and between all graphs, such that between all R regular graphs.
You can draw Colloquium.
Sorry.
You can draw Colloquium.
Yes, I will use it. So between all graphs, between all R regular graphs, we pick one uniformly at random. So this is a random R regular graph, and there is a result by Funtulakis and Panagiottou. They show that for random R regular graph, this process for the discrete time rumor splitting, the process completes after this steps. So this is, we have this perfector of log n times log n plus something small compared to log n. So this is just this is a perfector which depends on the degrees, and in a joint work with Drive and Lelarge, we show that for our regular graph, for continuous time model, this process will complete with this perfector times log n. So we see that for our regular graph. So this is a picture which shows this perfectors for continuous time and discrete time, and we see that the continuous time is faster than discrete time model. Okay. So the red one is for continuous time, and the dashed one is for discrete.
So what's the intuition? Why does continuous time complete faster?
So we will see. I will explain what is the next slides. Okay. So
actually, what it means is also that when the average degree of the graph increases, that's even faster. Is this what it's saying?
yes.
Understand correctly?
Yes. When you have more connectivity, it should be faster as well.
Whereas the other one doesn't really depend that much on connectivity after a certain point.
So this will be again decreasing, but yeah, this is faster. Because which is normal when connectivity increases. You will infect one of your neighbor more quickly, and I mean connectivity decreases the time needed to infect whole population. Okay.
But what is the intuition? Why it would be much faster with when you have weights?
So I will explain maybe in the next slide.
Times is spread into many neighbors.
Okay. So now I will explain the impact of introducing edge weights on distances in random graphs. Then we will come back to look at the rumor spreading problem at the end of the image. Okay. So for a graph G, and assume two nodes A and P, the distance is just dependent on the number of edges between these two nodes. And the diameter we define as the maximum distance over all pairs in the same component of the graph. When we associate weight WE to each edge E of the graph, the weighted distance is defined as the minimum weighted path between A and B. The weight of a path is just the sum of the weight over all edges of this path. And we define the weighted diameter again as maximum weighted distance between all pairs in the same component. And we define also weighted flooding time. We'll see for regular graphs, this will give us results for continuous time rumor spreading. So the weighted flooding time, if we fix one node, which has information at the beginning, for example, node 1, then we take maximum over all other nodes. Okay, so we get maximum weighted distance between one fixed node and all other nodes. Okay. So the case of complete graph has been studied by Svante Johnson. Show that, so assume that we put exponential 1 weights on the edges of the graph. So the result is more for other weights as well, but here what we would be interested is for exponential 1 weights. And we show that we have these asymptotics. So the weighted distance between two fixed nodes, 1 and 2, is asymptotically log n over n, and the weighted fluting time is 2 log n over n, and the weighted diameter is 3 times log n over n.
Can we get something to get a limit equal to 4?
Good question. I don't know. I don't think so. Yeah. Maybe I can write some calculations to find these results, and this will help us to understand what's happening. Let me show this result, how this works. So I assume that we look at the weighted distance between node 1 and 2, for example. Let me first prove this one. This is easier for fluting time. So we fix node 1, and we look at the maximum weighted distance between 1 and all other nodes. So this will have n minus 1 neighbors on the graph. Then T1, let me define T1 as the time needed to inform the first node. Okay. So what is the distribution of T1? We have n minus 1 exponential with parameter 1, and this is the minimum of this n minus 1 exponential, which will be exponential with parameter n minus 1. It's average 1 over n minus 1. So this will be exponential with parameter, right, the average 1 over n minus 1. So how about tk? So when we have already k nodes here, when we have k nodes here informed, the time needed to infect the another node. So it depends on how many edges. We got a memoryless property of exponential. So this will depend only on how many edges are going outside this set, which is k times n minus k outside this set. And then this will be minimum of this exponential, which will be exponential with parameter 1 over k times n minus k. Is it clear? Okay, so tk would be like this, and for fluting time, we should just look at the, let me define Sm as sum of this tk, k from 1 to m. Then fluting time will be, we should look at Sn minus 1. Okay? And so and let us look first at expectation of this, well, of Sn minus 1. This will be, so the expectation of this will be sum over k from 1 to n minus 1. This is correct. Okay. Which is simply, so we can write this as so we can see easily that expected of Sn minus 1 is 2 times log n over n, or something small compared to. We can also calculate variance of Sn minus 1 and then use Chebyshev inequality to show that including time, is close to 2 times log n over. So how about the first asymptotic? Let's write for the weighted distance between 1 and 2. Okay. So to see the weighted distance between node 1 and 2, we should condition on how many nodes are infected. So starting from node 1, how many will be infected before node 2 becomes infected? Let n be number of infected before node 2 becomes number. So if you define n as the number of infected before node 2 becomes infected, then we will have the weighted distance between 1 and 2 as the sum over k from 1 to n minus 1. Tk, indicator function of n is greater about k. Okay. And then again we can find the expected value of this, which is will be expected Tk times probability that n is greater equal k, and we can show that this is equal 1 over n minus 1 sum 1 over k, and so which is log n over n plus small comparing to n. Okay. And again, it is easy to compute the variance of this value, this parameter, and to show by Chebyshev inequality that we have this asymptotic. Okay. Okay. But the calculation for the weighted diameter is more involved. So what we should do, we should first prove that this is the upper bound for this asymptotic, and this is an lower bound, showing that there exist 2 nodes at least with this asymptotic. Okay. So let me write just upper bound for this, for the weighted diameter. Assume that y I define yi as maximum weighted distance between I and j, so the maximum is taken over all j. And okay, so we calculate the distribution of yi for this asymptotic, and we can indeed use this distribution to show that we have following large deviation results. So we show that yi is a sum of exponential, so then we can use and show that we have these large deviation results. I'm not going through the details, but using the distribution of yi, which was the sum of the exponential, you can show that probability that yi is greater than, for any a positive, greater than a times log n over n. You will have, this will be of order of n power 2 minus I times log n. Okay. Then the weighted diameter will be maximum over all I by I. Then we should look at this maximum. So this has the same distribution as weighted diameter and probability that this is greater than a times log n. We can use union bound to show that. So this will be smaller than probability that each of yi is bigger than this, and then we found that this is smaller or equal at n times this. Okay, so this will be order of n power 3 minus 8 times log n. Okay. Then when a is bigger, slightly bigger than 3, we see that this is small, and that's why this is an upper bound for the weighted diameter. Is it clear? Okay. Okay, let me continue. So let me talk about some probabilistic modeling of complex networks. So during the last decade, several methods has been proposed by probabilists to model complex networks. The first model, which is the simplest imaginable one, was introduced by Gilbert and Erdős in the late 1950s. So assume that we have n nodes and edges appear independently with some fixed probability p. And second model, so we can generalize this model and let's consider inhomogeneous random graph model. So in this model, again, the edges appear independently, but the nodes can have several types. And the probability that a node of type I is connected to a node of type J will depend on their types. So we have also professional attachment model, which is a dynamic random graph model. But what we will be interested in this talk is about configuration model, which is a model to construct a random graph with given degree sequence. So what is this model? Assume that for each n, we are given a sequence of non-negative integers, di, 1 to n, such that the sum of di is even. By means of the configuration model, we define a random multigraph with these degrees, which will be denoted by G star. And this is constructed as follows. So di will be the degree of node I. This is fixed. What we do is the following. To each node I, we associate di labeled half edges, and all half edges need to be paired to construct the graph. And this is done by a uniform random matching of them. When a half edge of node I is paired to a half edge of node J, we interpret this as an edge between I and J. Is this clear? Okay. So note that the graph constructed by configuration model may not be simple. We can have self-loop or multiple edges, definitely not. But conditioning on the multigraph being a simple graph, we obtain a uniformly distributed random graph with these degrees. Okay. So this is not hard to show that if we condition on simplicity of this algorithm, we obtain a uniformly distributed random. So our result will be about this graph and the weighted distance on this random graph model. Okay. We will assume several regularity conditions on the degree sequence. So we assume that for each n we are given di, and which has the following property. The first condition says that there exists a probability distribution PR, such that the fraction of nodes having degree r converge to PR. when the size of networks goes to infinity. We assume that P has finite mean, so the average degree will be finite. And we also assume that the second moment property, which says that the sum of di square scales at most linearly with n. Okay? So there is a result by Svante Johnson who showed that the second moment property assumption ensures that the probability that the graph constructed by configuration model is simple will be positive. Okay? So that's why we assume this property. And indeed, if we prove that the property holds with high probability for the graph constructed by configuration model, this will hold also with high probability for a graph chosen uniformly among all graph with these degrees. Okay? With high probability, I mean with probability tending to 1 as size of network goes to infinity. Second question here? Okay, so let us look at the local structure of this random graph. Assume a random node, so this node will have degree k with probability pk. How about the other generation? So indeed, this will not be true for the second generation because the nodes with degree k are k times more likely to be chosen for the second generation. Okay? Then we need to introduce the size bias distribution. So what we do, we approximate the local structure of the graph by an appropriate branching process. The first generation has degree k with probability pk, and from the second generation, each node has degree k with probability qk, which is given by this formula. So this is size bias distribution because the node with degree k are k times more likely. And note that by second moment property, such a Q has finite mean. Okay. So if we look at the mean of the size of generation k of this branching process, this will be lambda times nu power k minus 1. So lambda for the first generation and nu for the others. Okay. And there is a result by Molloy and Reed and Johnson to show that the condition nu greater than 1, which is the condition such that the branching process survived, is equivalent to the existence of a giant component, the size of which is proportional to n, in the graph constructed by configuration model. Okay? So we will assume the following, that nu is greater than 1, such that we are super critical setting. Question? Okay. Let us look first at the typical distance in this random graph model. So assume we pick two uniformly chosen nodes in the giant component of this random graph. Then there is a result by Renko van der Hofstadt and Scotchard. They show that we have this asymptotic for the distance between two nodes. Okay? So let me give you heuristic why we have this asymptotic. So we can see this by looking at the branching process. So this branching process, starting from A, at generation k, this will have size in expectation is lambda mu power k minus 1. Okay. And so when we look at which generation this will have size of order of n, this will be a generation 1 over log of mu. Okay. So that's why we have this asymptotic. How about the weighted distance? Assume that we put exponential 1 weight, i.i.d. exponential 1 weight on edges of the random graph constructed by configuration model. Then there is this result proved by Shankar Hamidi and Remco van der Hofstadt, etc. So for configuration model and also for Hertzsprung random graphs, they show that we have this asymptotic for the weighted distance. They consider the case minimum degree greater or equal to. So in this setting, almost every node will be in the giant component of the graph. And so there exists a distribution V such that the weighted distance minus log n over nu minus 1 converge to this. So the proof uses the limit of continuous time branching process. We have so this is quite easy to give a heuristic by looking at the continuous time branching process. And because of timing, I will not give this. So comparing this to typical distance between two nodes, we see that this is smaller. Okay, when we pick two nodes uniformly at random, the weighted distance between these two nodes is smaller than the typical distance between these two nodes. Okay. How about the diameter of the graph? So to consider the diameter, we need some extra definition. Let us denote by GQ that the generating function of distribution Q, and we assume a Galton-Watson tree with distribution Q, XQ. And then in this Galton-Watson tree, the extinction probability will be the smallest solution of the fixed point equation beta equals GQ beta. And furthermore, we define beta star as G prime Q of beta. Okay. Indeed, this parameter will play a role in the formula of diameter of the graph. Okay. So let me give you intuition behind this parameter beta star. So what will be? So assume we consider the set of particles of xq which survive. So we denote this set by xq plus. Then xq plus will contain the root of the branching process with probability 1 minus beta. So recall that beta was the extinction probability of branching process. And this will be empty otherwise. Okay. And if D is a random variable with distribution Q, then we denote by dp the thinning of D, which is obtained by taking D points and then randomly and independently keeping out each of them with probability P. So this will be binomial. Okay. Then the number of surviving children will have distribution D1 minus beta. Okay. And if we denote by D plus the offspring distribution in this branching process, which we condition on surviving, then we have probability that D plus equals 1. This will be probability that D1 minus beta equals 1, condition that this is greater or equal 1. And this is quite easy to show that this is exactly beta star that we defined. Okay? So let me give you a picture. So assume a branching process with distribution Q. Then what's happening? So if we remove, so we condition all nodes that survive, which means that we remove all other nodes, and then beta star is the probability that the node has just one child. Okay. So in this branching process, the probability that this branching process consists of a single path until generation k, when we remove all other edges which doesn't survive, is be exactly beta star over k. Okay. which is so the probability that this branching process staying thin for k generations will be beta star power k. Okay. So here is a formula for the diameter of the graph. This was studied by Borovach for the random regular graph and results for configuration model by Ferfors and Chandran, and for Erdo-Shreni random graphs by Riordan and Cornell. So what is this result? So here 1 over log mu is the typical distance between two nodes chosen uniformly at random, and we will have extra terms because of considering the diameter of the graph. Okay. So for the case that minimum degree is greater or equal to, you will have the same asymptotic for the diameter of the graph and the typical distance between two nodes. But when we have minimum degree equals to, we have this extra term. So indeed what happens here is the following. So let me define first k core of the graph. So k core of the graph is the maximum induced subgraph such that every node has degree at least k. Okay? To find the k core of the graph, we remove all nodes having degree less than k, and we continue this until all nodes have degree at least k. Okay? So when the minimum degree is greater or equal to 3, we have the weighted diameter will have the same asymptotic as typical distance. But when minimum degree is equal to, what happens here is that there exist two nodes with long distance 2. So assume that this is 3 core of the graph. In this set, every node has degree at least 3. Then here we will have long path until 3 core of the graph. And there exists another node also with long path to the 3 core of the graph. And the diameter will be between these two nodes. Okay. And the length of this path will be 1 over 2 times log a q1. Okay? So q1 was the probability that the branching process has one child, and that's why here the probability that this goes to until k generation, this branch, by looking at branching process, will be q1 over k. And when q1 is, so the probability that this has size 1 over 2 this will be of order of n minus 1. So by looking at branching process, we can show that the probability that we have the number of the generation of this path will be of this size. This will be of order n minus 1, and that's why we will. So we have of order n nodes, and that's why we will have some nodes having this length to arriving to 2 core of the graph. Okay. And what happens for the case when minimum degree equals 1? So indeed, this is we can show that 3 core of the graph is connected with high probability for the graph by configuration model, and then the 2 core of the graph will be some nodes which are connected to 3 cores, and also some small cycles. Okay. So this will be the 2 core of the graph.
graphing. We have this tree core, some nodes connected to tree core. We have some small cycles, and the graph will be, so here we will have some nodes connected to two core of the graph. So we can have also like this. There will be some tree attached to two core of the graph, and there will be also other components will be just tree. We will have also some other trees which are not connected to two core of the graph. 10 minutes. Okay. And here is our result for the weighted diameter of the graph. And okay. So again, we will have different asymptotic depending on the minimum degree of the graph. But when the minimum degree is greater or equal to 3, we will have this extra term as well, contrary to the diameter of the graph. And for minimum degree equals 2, we will have this extra terms, and for minimum degree equals 1, we will have this. Okay. So if we compare these two asymptotics, the weighted diameter with the diameter of the graph, so we saw that the typical weighted distance here is smaller than typical distance of the graph, but the extra terms here will be larger than extra terms for diameter of the graph. Okay. So this will depend case by case which will be smaller or larger. Okay. And let me give you some ideas of proofs of this result. So what we do here is that, the main idea is to construct the graph and look at the distance simultaneously. So instead of taking a graph and random and analyzing the balls around each vertex, we use a coupling argument which allows us to construct the graph and look at the balls simultaneously. And there will be 3 different cases to consider, depending on minimum degree of the graph. Let us denote by this extra term by Sn. So the proof will be, we will first prove that this bound is upper bound and then this is lower bound. The proof of the upper bound will consist in defining 2 parameters, alpha n and beta n. So what we show is that the following: the 2 balls of size at least beta n intersect almost surely. So we assume that they have n nodes. So starting from one node here until having this ball size beta n, and starting from another node, when these 2 balls has size at least beta n, these 2 balls will intersect almost surely. This means that we only need to control when the balls around a vertex will reach size beta n, and then we show that the times needed to go from size alpha n to beta n will be the same. We have the same asymptotic for all nodes of the graphs, and this will be similar to the typical weighted distance between these 2 nodes. And then the time needed to reach size alpha n will be upper bounded by this extra term, 1 plus epsilon of extra term, which depends on the minimum degree of the graph. And to obtain the lower bound, we show that with high probability, there exists at least 2 nodes with degree d min, such that the time needed for these 2 nodes to reach size alpha n will be larger than other nodes, and will be at least 1 minus epsilon Sn. Okay? So here we can see what will be these two nodes. So for example, for the K minimum degree equal 1, there will be a long path connected to two core of the graph. And there will be another node with long path connected to two core of the graph. And so the time needed to reach this node will be the extra term that we need. And from here to here, we do the typical weighted distance for this unit. Okay? Okay, so let me go fast. So here, this is what I said. The actual value for parameter alpha n and beta n will be this value. So alpha n is some power of log n, and beta n is slightly larger than root square of n. Okay? Then what we show is that with high probability for all nodes u and v, the mean u and v is upper bounded by the time needed starting from u to reach size beta n plus the time needed starting from v to reach size beta n. Okay. And we have this large deviation result for the time needed to go from size alpha n to beta n. Okay, then we will consider three different cases. Okay, so for the case when the minimum degree is greater or equal to 3, show that the graph is connected with high probability, then starting from any node. So i.i.d is the time is the size of the component starting from A. So the component containing A. So we show that probability that indeed the graph will be connected with high probability. So this will be greater than alpha n, and we have this large deviation results for the time needed to reach size alpha n. And so we show similar large deviation results for different cases. Okay, so again, this will be important, the two core of the graph, to consider the two core of the graph. And then conditioning on each node is connected to two core of the graph or not. This node is the component which is just straight, because for the diameter we need to consider the distance between all pairs of nodes, not just the two uniformly chosen nodes. For the lower bound, we proved that there exists at least two nodes such that they give this asymptotic. Okay. Okay. So before talking about this, let me go back to the rumor spreading problem. And to see why rumor spreading problem is connected to the floating time of the graph for the case of regular graphs. Okay. So we define continuous time rumor spreading. Assume we have a regular graph G or regular graph. Okay, so we have n nodes and each node has degree r. And continuous time, we define the continuous time rumor spreading as following. So initially one node is informed, node 1, and each informed node has a continuous has a clock with distribution Poisson parameter 1, and when node wakes up, he contacts one neighbor uniformly attracted. If we define T1j, the time needed to, starting from node 1, the time to inform node j in the graph, indeed this will have the same distribution as, So we have two models. This is one model. Let me write this like i.i.d, continuous time rumor spreading. And the second model is first passage percolation model, where we put i.i.d exponential on the edges of the graph. And so here, each node has Poisson with parameter 1, which means that, okay, when we use this edge, will be somehow exponential after times exponential with parameter r, so 1 over r. So the claim is that if we put exponential with parameter 1 over r on the edges of the graph, then the weighted distance between node 1 and j will be same as the time needed to inform j in the continuous time rumor spreading problem. Okay? So we have the same distribution. They are not equal, but they have the same distribution for the case of regular graph. Indeed, we can define the weight on each edge of the graph as the time needed that this node sends the information to his neighbor. Okay? And then we can show that these two models are equivalent for the case of our regular graphs. I mean, to consider the time needed for continuous time rumor spreading, we should look at just the weighted distance for first passage percolation in the case of our regular graph. Okay? And another result here is that, so here in a joint work with Yuval, we are interested in the number of edges on the shortest weight path between two nodes. Okay? Not the weighted distance, but how many edges are on this path. Okay? And there is this result for two uniformly chosen nodes, 1 and 2. So we have again asymptotic limit by looking at the branching process. And with Yuval, we show that we have this large deviation result when we take maximum over all j, and we look at the number of edges between 1 and j, and also the Hopcon diameter of the graph. So here what we prove first again that this is an upper bound and lower bound, and so I don't have time to talk about the proof of this. And so just I give you some few directions for each of them. So the open questions here is, so we proved Hopcon diameter for only, we were able only to prove for the case of our regular graph, okay, when all the grids are the same. But for the case, for general case, configuration model with different degrees, we don't know what will be the large deviation results. And for asynchronous rumor spreading, we have only this equivalence for the case of our regular graph. But when the degrees are different, indeed, these are not anymore equivalent, and we will have somehow the first passage percolation with the weights on the edges with parameters which will depend on the degree of each node. Okay. So there will be different weights. There will be exponential again, but this is not anymore i.i.d, but this will depend on the degree of each node. And there is not result for general random graph model on a continuous time rumor spreading. And also this would be nice to consider different weight distribution to see, for example, which distribution of weights will give us faster rumor spreading, or even to give asymptotic for the typical weighted distance between nodes, etc. Thank you very much.
Questions?
Yes.
Is it known how far, if you take a node outside of the Jan component, how far is it likely to be
How far is it to?
from Jan component?
You mean the other components of the graph? So
Well, you take something outside of it. How many edges do you need to add?
okay, so we have actually this result. Okay. How many? Okay, we have this weighted. Okay, here we show that the weighted distance between the node outside the giant component of the graph is upper bounded by this value. So this will be some prefactors of log n.
So I have a question. What happens, so in the last model, so if you can go back to the open questions.
Yes.
So what happens if, so I'm thinking about multigraphs, and for example, what if between 1 and 2, let's say you have 1 and 2, or you have 2 nodes, and you don't have just one edge, you have multiple edges. And if let's say that in your rumor spread, you're convincing your other node just only if you have set on both edges. Are there any results on this? So would there be like an equivalence between that and some kind of some weights, or would you collapse the multigraph to some kind of simple graph that with certain weights that the
No, I don't think there is any result from multigraph for general graph model or rumor spread. So a result from complete graph and some other models, but that's multigraph.
Because maybe if you have multigraph, then maybe you get rid of this problem of having different distributions, and then just somewhat happens.
You mean you have multiple edges on it? But so when you have multiple edges, you can replace it here by one edge. If you take the minimum of these edges.
Yeah, but
Or
oh,